All right. So today's schedule is I'm going to give you a retake of the last quiz, which will be the last 20 minutes of class. And we'll be covering, we'll be covering section 10.3 in the textbook today on hypothesis tests for population proportions. So I'm going to actually have two PDFs that I will be posting later today. The first one is the review of what we did last time. The second one is the 6-step process for doing a hypothesis test for a population proportion. I'll go through that with you today. Now, the PowerPoints are very long. I'm not going to go through the PowerPoints, go through a few of the slides, but not all of them. I highly recommend that you read chapter 10, sections 1 through 4. The first two sections we covered last time. Section 3 we're covering today, section 4 on Thursday. The other sections you're not responsible for chapter 10, just 1 through 4. But I highly recommend that you read the textbook and go through the examples after you've listened to my lectures. Now the PowerPoint, again, very long. I think there's like 58 slides for section 3. I'm not going to be able to get through even half of those, just a few of those. But the slides are okay, but I highly recommend reading the chapter and going through the examples. It would be better. The slides are just a summary of what you see in the chapter. So better to read the chapter, go through the examples. Now, next time, we'll have obviously more time in class because there's no quiz. So I'll show you a couple of examples of hypothesis tests for both proportions and for population means. But again, because of the limitation of time, and our class time is not an hour and 45 minutes. It should be a 4-credit course, but it isn't. It's 3 credits. So a lot of the responsibility goes on to your end to actually read through material. There's many, I'll assure you, there are many YouTube videos out there show you how to do hypothesis tests for both using your TI-83, 84 calculators, many of them out there, which you could also look at if you wish. But the 6-step process I'm going to take you through, it's step by step, and even on a test, I take you through many of the steps in the 6-step process for each of the problems. So it's for me, excuse me, it's the best way of learning this. I know other teachers teach calculator steps, which there's nothing wrong with teaching calculator steps, with the exception is I've tutored students who've gone through those types of courses. They have no idea what they're doing, literally no idea. And when they run into a word problem, they get completely lost, even though the calculator steps, the calculator has different features that do hypothesis tests, and they're shortcuts, but they really have no idea what they're doing, and they don't know how to interpret or read the calculator correctly. It's a mess, and I don't find that a good way of teaching this. So I'm going to teach you in my view, the proper way of learning this. And as long as you go through the textbook and go through the videos, see the videos that we do in class, and do the homework. There will be homework for this, which will come later in the week. If you do all of that, you should be okay. Because I don't get very complicated when I do hypothesis tests in a test. It's basically straightforward, 6 steps, all of that. And anyway, so let's get started. The first thing I want to do is show you the review of last time, which I put into a PDF, sort of the basic things that you need to know, plus a couple of other things that you need to know for doing hypothesis tests. All right, so I'll share the screen with you and pull up the PDF. So I'm going to actually go to the other one here. Again, both of these PDFs are Not posted currently, but they will be posted later today, along with the video for today. Basically, this TDF is called Basic Facts of Hypothesis Tests. All right. And one of the most important ideas is that these are hypotheses about claims about the population, either in our case, either a population mean or a population proportion. That's it. They have nothing to do with samples. The samples are used to determine if our hypotheses are valid or not, but the claims themselves are not about samples. They're about populations. So they're sort of like guesses. All right, this is my guess of what the population value mean should be or population proportion should be. Now, when you do a hypothesis test, once again, there are two hypotheses. One is called the null hypothesis. Again, this is a review from last time. It's basically, in most cases, it's the accepted hypothesis that researchers accept or people in society accept. And it's the one that we will consider to be true until proven otherwise. All right, we're going to consider the hypothesis, the null hypothesis, to be true. It always has an equal sign. So we're going to always state the null and alternative hypothesis symbolically. If you, on your final exam, there's always a hypothesis test on a final exam on the core piece. If you write it out in English, don't use symbols, you will get 0. I don't care if it's correct. You will get 0 for it because that's the way they grade it. They want to make sure that you know what we do symbolically when we create a hypothesis test. Okay, so the null hypothesis is always written with an equal sign, and the symbol that we use for the null hypothesis is H with a subscript 0. You can pronounce it either H0 or H sub 0. Examples, these are examples of null hypotheses. Typically, you write H sub 0 first, and then you put a colon, and then in this case, for a population mean, you're going to use the Greek letter mu. Now, in Canvas, when you're going to type this in your final exam, there is available to you symbols that you can use for all of this. I'll show it to you next week when we do a review. I'll spend a few minutes to show you how to use Canvas to type in what you need to type in. So, mu, this is H0. Mu is equal to 5 is one example. The mean, population mean is equal to 5. Another example would be H0 colon P, which is, of course, the population proportion is equal to 0.35. That's another example. So we always, and this is the very important thing, we always use population parameters in hypothesis tests. So we're always going to use, if it's a mean, we're going to use this Greek letter mu. If it's a proportion, we're going to use the P for population proportion. The alternative hypothesis is the other hypothesis. It's competing with the null hypothesis. Typically, it's the researcher's hypothesis that challenges the null hypothesis. You never use an equal sign in the alternative hypothesis. We either use greater than, less than, or not equal to, depending on the problem. The words in the problem will state which one of these three we will use. All right? It's pretty usually clear in the problem. I'm not going to say to you, use, in a word problem, I'm not going to say, use a greater than sign or less than sign. No, I'm going to give you a word problem, and then you're going to determine which of these three it is. So it's just a little bit of reading you have to do. The symbol for an alternative hypothesis is H sub A for alternative. And there are three types of alternative hypotheses. Either you're going to have greater than, less than, or not equal to. And these are examples of those with using mu for population mean. And then for a population proportion, obviously we use P. And these are three examples of those. So only one of these is going to be used in a particular hypothesis. So the null hypothesis will have an equal to sign. Okay? And the alternative hypothesis will have one of these three signs. Not all three of them. Doesn't make any sense, all three of them. Just one of these, depending on the problem. So the wording of the problem will tell you whether it's going to be greater than, less than, or not equal to. Once again, we assume the null hypothesis is true until we have enough evidence to think that it's not. And in general, what a hypothesis testing, the testing procedure that we're going to learn, is going to do is we're going to take the sample data, either the sample mean or the sample proportion. We're going to see if there's enough evidence. We're going to call it statistical evidence to reject the null hypothesis and support the alternative. Right? That's the way we usually say it. We are either going to reject the null hypothesis and support the alternative. If there's enough evidence, this statistical evidence, right, we state that the alternative hypothesis is probably correct. We call this, by the way, statistical significance. We say that there's enough that the sample statistic is significant enough to say that the null hypothesis is probably not correct. I'm saying probably because it could be. And the alternative hypothesis is probably correct. Now, if there's not enough statistical evidence, then we state do not reject the null hypothesis. And this is very important because I do see students still do this in the final, even though I say this over and over again. If we don't have enough evidence, we never, ever say we accept the null hypothesis. If you write that down, type that into your final exam, you will get 0. Even if you got the correct conclusion, you'll get 0 for that part of the problem. Because you cannot say I'm accepting the null hypothesis. First of all, it just says equal signs, so it's not really saying much. But we don't say accept because it's possible that even though there's not enough evidence in the sample to reject the null hypothesis, it could still be that in reality the null hypothesis is false. So we never say this, and if you say it, you're going to get 0 for that part of the problem, and it's a shame because when I say it, I know students understand what they're saying, but they still say this statement here. Never say this. All right, so we never say. I put it on. I underline it. I put it in quotes here. You can print this out, have it next to you in the final exam, and if you write this down, it's really your fault. You should never write this ever in any hypothesis test. I accept the null hypothesis. All right, questions about that because that's really important for you. It's really important. Here is a box which contains the idea of errors that are done in hypothesis tests. On the top here is the unknown population reality. Unknown because otherwise, why would we do a hypothesis test, right? If we know the population mean or proportion, there's no need to do any testing. But if it's unknown, then we do the test. Now, we were hypothesizing about the population parameter. Now, in reality, the null hypothesis is either going to be true or it's going to be false. Okay, that's the reality. It's either true or false. On the left side here is the results of our statistical test. So if our test tells us to reject the null hypothesis, right, and the null hypothesis is actually really true, then we made an error, right? That's called an error, and it's called a type 1 error. That's the name of it. Now, if we reject the null hypothesis and the null hypothesis is really false, then we've made a correct decision. On the other hand, if our statistical test tells us not to reject the null hypothesis and the null hypothesis is really true, then we've made a correct decision. However, if there's not enough evidence to reject the null hypothesis, but the null hypothesis is really false, we've made another type of error called a type 2 error. Now, on the right side here, alpha is the probability of a type 1 error. So if we reject the null hypothesis, and the null hypothesis is really true, and we don't know that, by the way, because we don't know anything about the population parameter typically. But if this is really an error that we made, we reject the null hypothesis, and the null hypothesis is really true, we've committed that type 1 error, and the probability of that happening is called alpha. It's a Greek symbol alpha, also called the level of significance. Now, if we do not reject the null hypothesis and the null hypothesis is really false, we've made a type 2 error, and the probability of that is called beta. And that's all we need to know about beta, all right? The definition of it, that it's a probability of a type 2 error. The actual calculation of that is a little bit more advanced. for you guys. It's something that typically it's done in a more advanced statistics course, or maybe in an introductory course at MIT or someplace like that, but certainly not at Rowan. So the only thing you need to know is what a type 2 error is, and also that beta is the probability of a type 2 error, and that's it. That's all you need to know about beta. We're not going to calculate it. The other thing is this other idea of power of the test. This is also an advanced concept that's done in a more advanced statistics course. But typically, it is 1 minus beta. So if you know what beta is, the power of the test is just the complement of it. It's just 1 minus it. Remember, this is a probability. So the power of the test is a probability. And it's the probability that the null hypothesis is rejected, given that the null hypothesis is really false. In other words, it's this upper right part of the box here, right, where we reject the null hypothesis and it's really false. In other words, we've made a correct result here. And by the way, researchers want this result. This is the purpose of doing their research. They want to reject the null hypothesis because they want to provide, see if there's enough evidence for their research claim. And of course, they want the null hypothesis to be really false, right? I mean, they don't want to make a mistake. So the power of the test is the power probability that they've made this correct decision, the one up here. And it's really, you want the power of the test to be high, right? You want the probability of a type 2 error to be low. You certainly want the probability of a type 1 error to be low. You want the power of the test to be high, because you want to have a high probability that when you reject, if you do reject the null hypothesis, that it's actually false. All right, and you've made the correct decision, and you jump up and down, and you've succeeded in your research. All right, so that's called the power of the test, and that's all you need to know about the power of the test. That it's 1 minus beta. So if I give you beta, you can easily calculate the power of the test, and you know that, and you should also know that a high number is what you want, a high probability. You want a low beta, you want a high 1 minus beta, and you want a low alpha. All right? You don't want probabilities of errors to be high. You want them to be low. Questions about that? So again, you'll have access to this. It'll be printed out for you. There's something like this in the book, but use this instead. This is really clear, I think, at least in my eyes, it's really clear. Now, what do researchers do in real life? Before they actually do their research, right? When they come up with, determining the size of the sample and things like that, one of the things they want to determine up front is an acceptable alpha, because, they're trying to reject the null hypothesis. That's their goal. They want to reject it. They want to see if there's enough evidence to support their claim. And they know, every researcher knows, that it could be an error, right? It's possible that the null hypothesis is really true. When they reject it, that's a type 1 error. So they want to make sure that the probability of a type 1 error is small at the beginning. So what they do, most researchers do, is they come up with an acceptable type 1 error, and it's really low. So typically they pick 5%, or maybe in the really hard sciences like chemistry and physics, maybe they pick 1%. But typically 5% or some other percent, right? Not anything more than 10% typically. So it's a low percent, low probability. It can be expressed as a decimal. So if it's 5%, it would be 0.05, or it could be expressed as a percentage, which would be 5%. So they determine what this alpha is up front. All right. Now, it says using this predetermined alpha, when they actually do collect the sample and do the research, they can determine if the sample value, this is the key point here, they come up with a hypothesized value for the population mean or the population proportion. Then they look at the sample mean and sample proportion for the actual sample. They've already determined what alpha is. And they want to see, using this alpha, and I'll show you how to use it a little bit later, they want to see if the sample mean or sample proportion is so far away from the hypothesized population mean or population proportion to make it unlikely that the sample value, sample mean or sample proportion, occurred by chance if the population mean or proportion is actually true. In other words, suppose the population mean is 100 and you come up with a sample mean of 80. All right. Now, most people, without knowing statistics, will say 80 looks like it's significantly lower. I'm going to say it's unlikely 100's the population mean. You can't do that in statistics. If I see that on a test, on your final exam, 0, because why even bother taking this course? You don't follow the procedure I tell you and the book tells you to do. There's a certain procedure to determine if 80 is sufficiently far away from 100. Don't just say it's something like, and I've seen students do this in the final exam when they do the written portion. They'll say 80 is much lower than 100, therefore I'm going to reject 100. You might as well not have taken the course. It doesn't make any sense to say that, all right? And just say it seems that way. Well, that's not what statistics says. It's math. That's statistics. You're just saying something that you would have said at the beginning of the course before you learned any of this. So don't say that, please. Don't say that. You go through the 6-step procedure I'm showing you. Now, the 6-step procedure will tell you whether you're sufficiently far away. That's the point. And according to the procedure, every single one of you will come to the same conclusion. All right. So, as opposed to a criminal trial, that was the example I gave last time. Criminal trial, some people will say, yes, there's enough evidence to convict the person, and somebody else might say, no, I don't think there's enough evidence. Then they debate it. Well, there's no debating here. You either do the procedure correctly and you come to the same conclusion, or you do it incorrectly and you come to a wrong decision. That's typically it. That's all there is to this. All right, so it's much easier than a criminal trial. Now, if it is sufficiently away, and then again, the procedure will tell you if it is, we reject the null hypothesis. That's the point. In other words, if the procedure says there's a 0.1% chance that this sample mean occurred if the population mean, if the sample mean is 80 when the population mean is 100. If there's a 1% chance that you would, when the population mean is 100, that you would get a sample mean of 80 or less, then 0.1% is really small chance of that happening. And that's what I mean by saying it's unlikely that the sample value would have occurred by chance. It's probably because the population mean is probably smaller than 100. All right. So that's the type of thing that we will learn how to do. All right. No guessing here. This is not guessing. Now, if it's not sufficiently away, according to the 6-step procedure that I'm going to show you, then your conclusion is do not reject the null hypothesis. And that's it. There's only 2 decisions here. All right. Either you're going to reject the null or you're not going to reject the null, and that's it. All right. So that is what I'm talking about. Now, the next page here in the initial handout has 3 types of hypothesis tests. 3 types. Now, one thing that before we look at these 3 types of hypothesis tests, I have a little note here in the corner, and this is described in the book. Now, again, read the book. It's very important to read the book, all right? But the book will describe this to you. Now, here is something called a p-value. P-value. P stands for probability, but they call it a p-value. And this is well known by many researchers in many fields, all right? Everybody knows what a p-value is in the research, who are researchers. What is the definition of p-value? It's the probability of getting the sample statistic or a value even further away from the hypothesized parameter. Let me say it again. It's the probability of getting the sample statistic or something even more or even further away from the hypothesized parameter. So let's do an example and I'll tell you what it means, all right? One type of test is called a two-tailed test. What is a two-tailed test? It's where the alternative hypothesis has a not equal sign, all right? So the wording of the problem could be something like, the current state of affairs is the mean is equal to 100, all right? but I'm a researcher. I don't think it's 100. Here, I don't think it's 100. Well, when I say I don't think it's 100, it could mean it could be less than 100, or it could be greater than 100. I'm not telling you which way. I'm telling you I don't think it's 100. So that's a two-tailed test, right? So the sample that you get could be values that are, now in this case I should say 10. All right, I said 100, I mean 10. All right, let's say I think the standard is that the mean is 10. I don't think it's 10. All right, and it doesn't matter what we're measuring here, something, but the value is 10. So one of the requirements of a hypothesis test is that the 10 that we're talking about has to match both in the null and alternative hypothesis. So the hypothesis test here assumes two hypotheses. The null is going to always have that equal sign, and the alternative will have the not equal sign, and these numbers have to match. They can't be different numbers. So this is a two-tailed test because the alternative is not equal to. And I came to that conclusion because in the problem, in the words of the problem, it doesn't say less than or greater than. There's no indication one way or the other. It's just, I don't think it's 10. So therefore you say not equal to 10 as the alternative. If there's no indication to the left or to the right, it's not equal to. All right. I hope that makes common sense, right? It's common sense. Now, what does that mean in terms of the sample data? Well, the sample data could be, the sample mean in this case could be a number that's less than 10 or greater than 10. Now, of course, it could be equal to 10, but it's unlikely. It's probably going to be less than or greater than. But in this case, I wrote two sample means listed here in case one of them is less than or one of them is greater than 10. They can't be both. You know, you're not going to get a sample mean that's both, obviously, right? Let's assume here that the sample mean here is 6, or the sample mean over here is 13. But the point is you're going to get one or the other. You only have one sample. The reason, again, I wrote this is that your sample mean is either going to be less than the population, the proposed population mean, or it's going to be greater than that. All right. That's what I wrote over here. The sample mean is either X bar star, which is the one that's greater than, or X bar double star less than. All right. Any good questions? I think we're good. All right. So that's called a left tail test. Now, what is this thing here with the p-value thing? What does that mean? Well, regardless of whether the sample mean is less than the proposed population mean or greater than that, what we're going to do is we're going to calculate the area either to the right of this sample mean if it's greater than 10, or the area to the left of this sample mean if it's less than 10. So one of these is going to be calculated. One of these areas. It's either going to be the one on the left or the one on the right. Again, depending on the sample mean. If it's greater than the population mean, or if it's not. But here's the deal. When you calculate this area here, remember the p-value is the probability of getting the sample statistic or a value even further away from it. Well, here, if the sample mean is greater than the population mean, right, area to the right here, we know how to calculate. I'll show you how to calculate that in a minute using normal CDF. But this area here is only going to be 1/2 the p-value. Because why? Because it's possible that you could have had a sample mean down here too. So what we're going to do is calculate one of these two areas and then double it. And that's why I say 1/2 p-value. So whatever you calculate the area to be, you're going to have to double it to get the true p-value in a two-tailed test. All right. Again, I'll show you how to do that in a minute. The other possibility is have a left tail test. Now, if you look at it before, I had mentioned that the alternative hypothesis says not equal to. The alternative hypothesis determines which of these three tests we have. If it's not equal to, it's a two-tailed test. If the alternative hypothesis is less than, it is called a left tail test. For obvious reasons, it's pointing to the left, the symbol, right? So in this case, I'm going to have a hypothesis test here for looking at a population proportion. I'm saying the null hypothesis is that the population proportion is 0.45. The alternative is that it's less than 0.45. Here's the area that is less than p hat. Now, what is p hat? It's the sample proportion. So once we run our sample and we determine that the sample proportion is some number, in this case, less than 0.45, all right, then the area to the left is going to be our full, complete p-value. It's the probability of getting this sample statistic or something even further away from 0.45, which would be the area to the left. And again, we're going to use normal CDF to do this. This is how to calculate this p-value. It's nothing new. We already know how to calculate probabilities off of a normal curve. This is a normal curve, by the way. Normal curve. All right, and then the right tail test is where the alternative hypothesis is a greater symbol. Again, here's an example here with population mean. Notice the alternative hypothesis has greater than in it. And the p-value, therefore, would be the area to the right of the sample mean. All right. And that's the 3 types of tests. All right. So 3 types of tests. Again, we have our two-tail test, left-tail test, right-tail test. Now, go out of here and go to a 6-step process. Show you this before we do our quiz. All right. 6-step hypothesis test for a population proportion. Suppose our hypothesis is about a population proportion. Now, I'm just going to use this as an example. P is equal to 0.72 was our null versus our alternative as P is not equal to 0.72. By the way, this is how you write it. All right, this is the symbols for it. And I hate to tell you this because I see students do this all the time, and I don't know why they do it. It doesn't make any sense. They leave the symbol out. They'll say equal 0.72 for the null. They'll say not equal to 0.72, and they forgot to put the P in. If you do that, you get 0 in the final exam. 0. I don't understand why you don't just make that little bit of more of an effort, but I see many students doing that. And I've never figured out why. It just doesn't make any sense. If you're going to write things down, write them completely. And so what's step number 1? State the null and alternative hypothesis. You read the problem, you figure out what the null and alternative hypotheses are, and you write them in this way. This is how you have to write them. Okay? You don't use p-hat, the sample proportion in the hypothesis. If you do that, you get 0 also. All right. When you state the null and alternative hypothesis, it has to be exactly looking like this. If it doesn't look like this, in the final exam, you'll get 0. In the next test that you have, it's multiple choice, so you'll be able to recognize. But in the final exam, when you actually have to type in these things, if you don't write them right in this way, you're not going to get any credit for this part of the final. That's step number 1. So you have to write the null and alternative. It makes sense, doesn't it? Because if you're going to do a hypothesis test on something, you have to know what you're doing it on. You have to know what the null and alternative hypotheses are before you do the test. It's common sense. Number 2. Now, assumptions for the hypothesis test. There are 2 assumptions. If you forget one of them, you don't get the full credit, again, for the final exam. All right. Number 1, and this is true for any hypothesis test, the sample was randomly selected. If the sample is not randomly selected, if it's a convenience sample, something like that, guess what? You're done. You cannot do any of the remaining steps. If the sample was not randomly selected, you cannot do a hypothesis test because if it's not randomly selected, you can't do probabilities, you can't calculate p-values. So this is one of the requirements in the core piece of the final exam. They're going to ask you to do both of these things. Now for proportions, here is the calculation you have to do in addition to it. You have to calculate, you have to take the n, the sample size, and multiply it by the hypothesized proportion, not the sample proportion, but the hypothesized proportion, in this case, 0.72. So if n is 1,000 and p, the hypothesized portion is 0.72, you get 720. As long as both of these calculations are at least 10, you can do the hypothesis test. If one of these is not 10, if it's less than 10, you can't do anything more. You're done. You have to find some other way of doing the hypothesis test. This is not going to work, what I'm showing you. All right. So in this example here, n is 1,000, p is 0.72. You calculate n times p. You calculate n times 1 minus p. Notice that np plus n times 1 minus p add up to 1,000. Makes sense, right? Ends up 1,000 people in the survey. Both of these numbers are bigger than 10. Now, I don't want to see the following on the final exam. All right, you say you do your calculations and you know what the answers are. And then you say something like np and n minus 1 minus p is greater than or equal to 10. And therefore, I can do this. I can say it's approximately the sampling distribution of sample proportions is normal. Guess what? You get 0 for that too, because you didn't show the calculations. Don't just do calculations. And again, on the written part of the final exam, write it down. Again, I don't understand it. Students, again, don't take that extra little step. All right, just take the step and write down what I'm showing you here. If you don't do show the calculations, you get 0. All right, even says it in the problem. You'll see it, something like that. It'll say, show your work. You don't show your work if you just simply make the statement, or you may even just say np at times n1 minus p are both greater than 10, and then you say nothing else. Well, you definitely get 0 for that. Right? Even if you calculate it correctly on a sheet of paper, if you don't show your work on a written part of the final exam, you get nothing. All right? I'm telling you, you don't need to get any credit for that, even if it's correct. So you have to show your work in the written part of the final. And I'm showing you how to do it. And I'm saying that once you show your calculations, you make a little statement at the end here. Since np and n1 minus p are both greater than 10, well, I can say it here because I've already showed you right above here my calculations. All right, so if I do the calculation, then make the statement, then I say the sampling distribution of sample proportions is approximately normal. That's why I can use the normal distribution for a proportion. Remember, proportions are not continuous variables. They are discrete. So the only way we can make them, treat them as if they're continuous is with this calculation, np and n1 minus p. Show the work, show the arithmetic, and then make your conclusion. All right, just like what I'm showing here. And shame on you, again, if you don't do that, because I'll have this posted and you can put this right next to you. And you can just type it in as you see with, of course, the correct numbers. This is an example of how to do it. Step 3. Once you're done that and concluded that you continue with steps 3 through 6, then step 3 is to calculate what's called a test statistic. Now, for proportion, this is the test statistic. Now, it's a z. It's a z-score. So what's in the numerator of the z? It's the sample statistic, the p-hat, minus the proposed or hypothesized population proportion. It's in your hypothesis test. In that step number 1, that number that you're showing me, that's p. In the denominator is the square root. This is the standard error. This is the standard deviation of the sampling distribution of sample proportions. That's what's in the denominator. That's the standard error. The square root of what? P times 1 minus p divided by n. Now, p in this case, don't use p-hat in the square root formula like you did with confidence intervals. With this, you put your population proposed hypothesized proportion in here. So 0.72 is p. You put that in here, just like you did in the numerator here where you see p. And then 1 minus p would be 1 minus 0.72, and then n would be your sample size. Square root of all of that is your denominator of the z. So Numerator is the sample proportion minus the proposed proportion. Denominator is the square root of all this stuff. When you calculate this, this is your test statistic. So if I ask for a test statistic, you're going to show your work. And by the way, on the final exam, you need to show the formula. Show this formula equal, and then plug in the numbers, and then put the answer. You understand what I'm saying? Show the formula, put equal to, plug in the numbers. You need to show that you plugged in the numbers, and then put an equal to and put your answer. Now, it may not say to how many decimal places. It's okay, 3 to 4 decimal places. Not 2, 3 or 4 decimal places. Write that down. It should be at least 3 to 4 decimal places. If you want to put more, you can, but 3 or 4 is fine. Once you have your p-value, you're going to, excuse me, the next step is to calculate your p-value. And I'm showing you how to do it right here. All right. If you have a two-tailed test, so you have to go back to step 1 and see, all right, alternative hypothesis, is it a two-tailed test? If the answer is yes, then your p-value is going to be 2 times normal CDF, that's your calculator function, and in parentheses, if your test statistic is positive, it's a positive number, it's greater than 0. Remember, a z has a mean of 0. So if it's greater than 0, it's going to be greater than the mean. Then we're finding what we're finding in normal CDF is the probability that z is greater, at least greater than that value. So we're going to put z star first, as if we're doing a right tail, which we are. We're right tail calculation. And then we use, for the end of the interval, use 1,000, and then the mean is 0. Standard deviation 1, because it's a z, standard normal. And notice we multiply it by 2. Remember, in that previous sheet that I showed you earlier, a two-tailed test, you're going to need to, this area that you're finding is 1/2 the p-value. So you multiply it by 2 to get the full p-value. Now I'm going to put or here because if your z star that you calculate in step 3 is negative, we treat it as a left tail. Normal CDF is a left tail, so we do our negative 1,000, then z star will come next, 0, 1. And again, we multiply that by 2. So one of these two is correct. If z star is greater than 0, use the first formula. If z star is less than 0, use the second one. And that's going to be your p-value. If it's a left tail test, treat it as a left tail, normal CDF. If it's a right tail test, treat it as a right tail, normal CDF, just like we've done before. That's step 4. Step 5 is your decision rule. Now, in the problem, you'll be given alpha. It'll always be given to you, alpha. Alpha is what? It is the level of significance. That's one term for it. It's the probability of a type 1 error. We can state it in 3 ways. I could say alpha. I could say level of significance. I could call it the probability of type 1 error. It'll be expressed either as a decimal or a percentage. But here's the deal. If the p-value is less than or equal to alpha, now, be careful. If you're expressing your p-value as a decimal, you have to express your alpha as a decimal. If you're expressing your p-value as a percentage, you're going to express your alpha as a percentage. But please, I would recommend just expressing it as a decimal. Both of these have to be expressed the same way. If the p-value is less than or equal to alpha, the decision rule is reject H0. Reject the null hypothesis, period. No thinking about it. That's the rule. If the p-value is greater than alpha, do not reject H0. So that's basically what you're going to write here in your decision rule. You're going to say p-value less than, for example, if p-value is 0.03 and your alpha is 0.05, you're going to say, since the p-value of 0.03 is less than alpha of 0.05, I'm going to reject the null hypothesis and just write it that way. All right? That's your decision rule. And finally, interpretation. The interpretation part of it is you're going to say something like at the S percentage significance level. So typically, if alpha is 5%, you're going to say at the 5% significance level. You must state the significance level in an interpretation. So typically you say it right at the beginning. At the 5% significance level, there is enough or not enough evidence, depending whether you rejected the null. You're either going to reject or not reject the null. An alternative way of saying this would be at the 5% significance level, there's enough evidence to support H naught, because if we're rejecting the null, we're supporting the alternative, or there's not enough evidence to support the alternative. That means we're not rejecting the null hypothesis. So there's two ways of writing that. And here's the deal for the interpretation part. You must write it in the context of the problem. If you just repeat step 5 and say, there's enough evidence to reject H naught, and that's all you say. At the 5% significance level, there's enough evidence to reject the null hypothesis. That's not the context of the problem. You have to state what the problem is asking about. You have to write the words of the problem in there. All right? You see what I'm saying? If the problem is about a reading program and the reading program, and there's something about the proportion of people who are successful in the reading program, you must write those words in there about the reading program, about what the alternative hypothesis, null and alternative hypotheses are in words. This is where you put the words in, right here. If you do not, if you're just repeating step 5, you get 0 for this also. An interpretation, that's not an interpretation if you say there's enough evidence to reject H naught. That's not an interpretation. That's just repeating step number 5. All right. So again, I will show you a couple of examples on Wednesday. Now, I'm going to show you on Wednesday another one of these 6-step processes, the 6 steps for a hypothesis test for a population mean. All right, I'll show you those steps with the correct sample statistic and all of that. I'll show you that at the beginning of the next class. All right, so it's 1:20 now. I'm going to stop sharing with you. The quiz should be out there. Give me a thumbs up if you see it. Remember, this is a retake, and your highest score is what will count. All right. Now, if you don't want to take it, it's up to you. You can accept your other score, and that's fine. But I would assume many of you will probably want to retake. All right, I'm going to stop the recording.